Hello. In this video we're going to talk about Hess's law. Now Hess's law is a law that allows us to measure enthalpy changes. So it allows us to do so when we can't directly measure it. So Hess's law is basically the energy change is independent of the path taken. So if we have, let's say, a reaction, and it is, we're going to make it red, and I say we have A plus B, and I react to give me C and D. So I want to measure the enthalpy change of this reaction, but I can't measure it directly for whatever reasons. They can't individually break the bonds, there's other energies being released, so I have to try to find a different way. So Hess's law allows me to find the enthalpy change for a number of sub-steps that eventually lead to the products. So I can get like this enthalpy and add it to kind of this enthalpy and add to this enthalpy. So I'll make this like 1, 2, and 3. So if I have those three together, they're going to equal my enthalpy change for the whole thing. So the path, which goes from here all the way to here, has the exact same energy as going kind of directly to there. So if I can't measure directly and I have other data that I can use, I can take that data and I can figure out the enthalpy change. So this actually is really useful. It's super useful. For one thing, it makes calculating enthalpies a lot faster if I have all the data that I need to. But also if like I can't measure, say, lattice enthalpy or other reaction change data, it's also very useful. So I want to take a look first off at, I'm going to move all this up here, move everything up. So my first example, I'm going to call it example 1. I'm going to look at the bond enthalpy data for a reaction. So bond enthalpy. So for the reaction, I'm going to something fairly simple. I'm going to look at the reaction of ethene, which is C2H4, and it's going to react with oxygen, which is an O double bond, and it's going to produce carbon dioxide, C, get this out of the way, O, let me just make this smaller, move it over, and I'm going to get also kind of two CO2s and 2 H2Os. So this reaction, it's going to be really hard to me to measure the enthalpy directly. I'm not sure about this energy change. It might be hard to do in a lab, so I don't know. So what I'm going to do is I'm going to use bond enthalpy data. Now bond enthalpy data is the amount of energy it takes to break a bond. So ostensibly, I'm going to take all my reactants on this side, and I'm going to break them up into their gaseous atoms. So I'm going to have 2 kind of carbons, I'm going to have 4 hydrogens, and these are kind of gaseous atoms. and I'm also going to have 2 oxygens. And I'm going to do the same to the products. So on the product side, I am also going to, and I'm going to make this black, break them into kind of the same gaseous atoms, because, well, the atoms don't go anywhere. Reactants turn into products. But the bond enthalpy data tells us the amount of energy it takes for me to break this ethene molecule up, and the oxygen molecule up, and the carbon dioxide molecule up, and even kind of like the H2O. So, first of all, I'm going to look at my data table, and I'm going to figure out which bonds I have and the data I have for them. So I'm going to look at my reactants first. So my reactants, and I'm going to do them in blue, my kind of delta H for my reactants. Well, I have one kind of carbon-carbon double bond. So I'm going to just kind of write that down. And I also have 1, 2, 3, 4 carbon hydrogen bonds. Now I also have 1 oxygen-oxygen double bond. So these are all the bonds I have for my reactants. On the other side, for my products, well, I have a carbon-oxygen bond, but I have 2 of them in my carbon dioxide molecule, but I have kind of 2 carbon dioxide molecules. So I got a grand total of 4 carbon-oxygen bonds. And I also have, I'm just going to move this over, and I also have 2 oxygen-hydrogen bonds, but I have 2 molecules of H2O, so in grand total I have 4 OH bonds, because each H2O is 1 bond, 2 bonds, and I got 2 of them total. So those are the bonds that I have. So I look at my data booklet, and I look at my table, and it says the carbon-carbon double bond is 612 kilojoules. So I'm going to write down 612 kilojoules. And this is all per mole. And I have 4 carbon-hydrogen bonds, and each carbon-hydrogen bond is 413 kilojoules. And an oxygen-oxygen double bond is, oh, actually, I have 2 of them. I forgot. On the other side, I forgot to balance it. So let me just go back up here. Just notice that. So 2. And I have 2 oxygen-oxygen double bonds, and they are each 498 kilojoules. On the other side, I have 4 carbon-oxygen double bonds, and each one of them is 746 kilojoules. Sorry about that. I'm going to highlight it, get rid of it here. Oh. Shoot. Go back to here. There we go. So I got 4 times 716 kilojoules plus 4 times OH is 464. 464. Yep, kilojoules. So now I'm going to just total it up on either side. So 612 plus 4 times 413 plus 2 times 498. Well, that's going to give me a grand total of 3,260 kilojoules. On the other side, 4 times 716 plus 4 times 464 gives us 4,840 kilojoules. All right, so I've totaled up both my reactants and products and all the energy that's contained within the bond. So this is the energy it takes for me to kind of either to break all these bonds into their gaseous atoms. Now here's the key thing. I have to go back up and I have to look at kind of the path I took. So to get from my reactants to products, and I couldn't take the direct path, I had to come down through the gaseous atoms and then back up towards my products. Now, when I made the gaseous atoms from my reactants, I went with the arrow. But when I went from my products to make the gaseous atoms, this is actually going against the arrow. Since it goes against this arrow, kind of down here like this, that means I have to actually flip the sign, so it's going to become negative. So, I'm going to write down my enthalpy for my reaction is going to be equal to the enthalpy of my products, my reactants, and it's going to be minus, because it went against the arrow, the enthalpy of my products. So I have 3260 subtract 4840, and in the end I get negative 1580 kilojoules per mole as my enthalpy for my reaction. And this just means that the energy it took to break the bonds is much more than the energy it took to make the bonds. That's why it's kind of negative. So, and we could also think about this in terms of our energy level diagrams. So, in an energy level diagram, so this is my energy. I have my reactants here. Those are reactants. And this is exothermic, so my products are down here. But in both cases, I had to go up to make the gaseous atoms. So my reactants, I should make them blue. Had to go up there. Products also had to go up there. And the difference, well, that is my enthalpy. So right now it looks like the energy it took to make the products is much greater than the energy it took to make the reactants, to break them. The energy it took to break the products is much greater than the energy it took to break the reactants. That's why it's negative. Endothermic, it's going to be the opposite way. So this is just the first example of Hess's law and how bond enthalpies can be used as alternative pathways to find the enthalpy of a reaction. In the next parts, we're going to take a look at both enthalpy of formation and also the enthalpy of combustion, and also explore an alternative method other than our kind of reaction triangle to calculate it out.